Now that we've talked about cylindrical and spherical coordinates, let's talk about how do we use them to do integration here. So we'll start off with cylindrical coordinates. If the 3D region, so this is only about triple integrals, the 3D region you're integrating over is most naturally expressed in terms of bounds in r, theta, and z. Consider switching to cylindrical coordinates. So what we're going to do is theta runs from theta 1 to theta 2. R runs from r1 of theta to r2 of theta. Z runs from g1 of r comma theta to g2 r comma theta. F of r cosine theta, r sine theta, z, r dz, dr, d theta. So big summary here is that this is just like polar coordinates, but with an extra z variable. Okay, so let's parse this here. First thing, order. We always go theta on the outside, then r, then z. We always go in this order. Sometimes you could move things around, but everything, you know, I'm quite certain that everything I'm going to give you can be done in this order. And the important thing here is that r needs to depend on theta. Just like in polar coordinates, we always, if one of theta and r depending on each other, it's always r depending on theta, so we have to integrate with r first and then with respect to theta instead of vice versa. Okay, what else do we see in here? Okay, so x is r cosine theta. So in your integrand, you need to, if you have an x, you replace r cosine theta. If you have a y, you replace y with r sine theta, and then you leave any z's alone. And then finally here, just like in polar coordinates, and for, you know, the same reasons as in polar coordinates, when you switch over to cylindrical coordinates, dv is equal to r dz dr d theta. So we need to fill in an extra, throw in an extra r in there. Okay, so that is the setup here. This is our generic principle. Let's do some examples. So first example here, integrate f of x, y, z is equal to z times square root of x squared plus y squared over the region given by x squared plus y squared is less than or equal to 4, z is between 1 and 5. Okay, so let's see here. This region is a cylinder. It's a cylinder. Z runs from 1 to z runs to 5. And the cross sections here are all circles. Cross sections parallel to the xy plane are all circles of radius 2. Okay, let's see here. What are our bounds here? Well, we already have z runs from 1 to 5. X squared plus y squared is less than or equal to 4 in the xy plane. That's just this. This is just a circle of radius 2. So r can be anything from 0 to 2, and we're going all the way around the circle. All of our bounds here are constant. Theta runs from 0 to 2 pi. So, okay, let's write down what is our double integral. Sorry, not our double integral, triple integral. Theta runs from 0 to 2 pi. Start with theta. Then r runs from 0 to 2. Z runs from 1 to 5. And what is left now? So our integrand is z. And then realize here, square root of x squared plus y squared, this is r. So z times r. And then we throw in the factor of r here. That comes from dv. So we have r dz, dr, d theta. So this is what we are integrating here. This is a very straightforward integration because everything here, all the bounds are constant. So theta runs from 0 to 2 pi, r runs from 0 to 2, r squared times z squared over 2, plug in 1 to 5, dr d theta. And I should point out here, we can actually factor this integral very easily. So theta runs from 0 to 2 pi, d theta times r runs from 0 to 2, r squared dr. This one breaks apart very, very easily. I guess I could have just done this for the starters here. I'm undoing a little bit here. This is 2 pi. This term right in here is going to be 8/3. And this term right in here is going to be times 24 over 2. So simplify that. That is your answer. Okay, so this is our first example of cylindrical coordinates. We'll definitely do a lot more in the near future.